how do I do that? Oh, okay, got it.
Yeah, it's works.
Okay, cool. Okay, so can you guys see the screen?
Yeah.
Yes.
Yeah.
Okay, okay. So we will cover folder for R and for the L prime. So I assume you guys know the definition, so we won't be going into all that much. And so first, a very simple example would be folder plus suppose some list let's so the starting value is 0 and then we have 1 till 10. Okay, can one of you tell me what this will be related to?
I'm 55.
Okay, so yeah, it's how did you get it?
And just adding 0 to each element.
Okay, so first we are starting from the right. Okay, so first we will have plus. Okay, let's not take plus like that. Okay, no, I think it's fine actually. Yeah, so plus of wait, yeah, no, we're actually 10 comma 0. That's the same. 10 comma 0. So that will return 10, and then we will have plus of 9 comma 10. That will return 19, and then we will have plus of 8 comma 19. This will return 27, and then okay, epic. So this was actually like since it's commutative, you won't have too many problems. So how about let's mix this up with folder of minus 0, and let's make it smaller. So 1 to 5. So does one of you want to do the dry run with me, or do you just want to say the answer?
It will be different because minus is.
Yeah, it will be different, definitely. So, okay, so let's start. So what will be our first operation?
5 minus 0.
Very cool. So we have minus of 5 comma 0, which returns 5. Okay. Then what will be our next operation?
4 minus 5.
Epic. That will be minus 1. And then?
3 minus negative 1.
Very cool. Which will probably be 4, hopefully. And then?
2 minus 4.
Okay. Which will give me minus 2. And then?
Minus sign I think will not be there in the 2 minus 4.
Wait, why?
2 minus
Oh, okay, yeah,
the minus
sorry, my bad. Yeah. Thank you. Yeah, so after this,
1 minus negative 2.
epic, which will give me 3, hopefully. So folder, this should evaluate to 3. Now let's verify that. Oh, wait, let's give me just a second. I will share my screen instead. So can you guys now see the VS Code screen?
Yeah.
Yes.
Okay, good. So what we're doing is we're doing 4 minus 0 and 1 to 5. I hope I got the syntax. Yeah, it's 3. Okay, so that's cool. Yeah. Now let's move on to some other examples. Yeah. Okay. So a very easy way to see the difference between folder and folder. Hopefully, easy way. Folder minus 0, 1 to 5. Okay. Why don't one of you help me do this also? What will be our first operation?
0 minus 5.
0 minus 1. Epic. That will give me minus 1. And our next operation?
Minus 1 minus 2.
Yep. So that will give me minus 3. Next operation?
Minus 3 minus 3.
Yep. Sorry. That will give me minus 6. Next operation.
-6, -4.
Minus of 6 and 4. Oh, sorry. Which is hopefully -10. Yeah. Next operation.
-10, -5.
Epic. So that's -15. So like, okay, let's just verify that once to see if we got it right. Whole del of -0 and 1 to 5. Yeah, that's -15. So that was a very simple example to see how folder and folder are different, like how different they calculate stuff. So that's cool. And okay, so Sir did stuff like identity function and then what else? Length of code and stuff. So yeah. Okay. So you guys also did folder 1, right? Where the first argument is actually the last element of the list.
Yeah.
Oh, okay, very good. So why don't one of you help me with this one? Find the minimum. Let's make it a even element in a list. Okay. So we can either start with the folder function or folder 1, and or we can first write a helper function, whichever we want to. Yes. Does anyone want to try? Okay. Am I audible?
Yes, you are audible.
Okay, good. So
We can sort
yeah.
the list and then take the head of that.
Okay, yeah, that's possible, but sorting will take you O(n) square or n log n time, right? So we can instead just, since it's just one element, we can just find the minimum even element by going to the response. And like as we said, we want to use for R1. Okay. So how about now?
In this mode to could do that and
Okay, yeah. So first, you can either have an anonymous function or a helper function. I would suggest a helper function. So let's write the helper function f of. Okay, so f will probably take an int, another int, and split an int. Okay, so someone define f for me. Wait. Sorry, I think I couldn't hear you. Can you repeat? Exactly filter, you can just use name. Okay, oh, someone typed in the chat. Sorry. Exactly filter even and name. Yeah,
to
filter
end
even and name
what
works.
this mode
Wait, your voice is cutting out. Can you repeat?
for A2 where I mean sorry f of AB is A div mod B.
A div mod. Wait. Okay. So you want div mod of AB.
Yeah. And then we
Okay.
could go f of A2. And see,
Then we could go. Oh, no. So that's not what I was suggesting. I was suggesting that this F will be the help. So like what we want to do is we want to do what we want to do is min even of suppose some list, just the input.
Actually, modulus will be
ls.
0, will be an even number, and we could search for,
Yeah, 0 is an even number.
yeah, and then we could search for the minimum of these two.
Yeah, so we want to, okay, so actually I don't think this is a good example for folder 1 because my last segment might not even right. Okay, so yeah, let's assume for, okay, so this is a bad example, but yeah, sure. Let us assume the list has positive possibilities. Assume list has positive elements. Yeah, so what we want to do is a folder of some helper function f, and then you say that the first minimum function will be 0, and then ls. So now we have to define f. So where f of x comma y. Yeah, now go ahead.
So f of xy is f of x, f of x, I mean, f of x div mod y. I was suggesting that we could take the auxiliary function div mod y and taking the elements, these elements will take suppose n, then n div mod 2. Then if modulus
Yeah.
is 0, that will be an even number, then the list of stores will be the minimum
If y
even.
greater than x, then y else x.
Just I'm just thinking the algorithm, but I
Wait,
don't know. Yeah.
Okay, no, that's fine. That's fine. I think someone else was suggesting something. Can you go again?
If y is greater than x, then y else x.
X equal to y. Otherwise, equal to x. This is what you're suggesting?
Yeah.
Okay. This will work to find the minimum element, but it won't find the minimum even element.
Yeah, I have a like idea.
Yeah, go ahead.
Yeah, so it's like we define guards, like we define like, whether if both x and y are odd, you can take it to be either of them.
Okay. So, x, wait, this modder thing in Haskell. Wait, I have to check. 5 mod. No, it is mod. No.
We can just use even
Mod
or
of
odd.
5 and 2.
You have to put mod in backticks. Or even is also fine.
Yeah, yeah.
So that would be too long, I guess.
Yeah, it'll be like 4 guards, like.
Is this screen frozen for everyone?
Even then.
Yes.
I think
Yeah,
he
he'll be
disconnected.
back.
Yeah, sorry. I'm very sorry. My internet is actually not very good. Arindam, can you enable screen sharing for participants? Oh, I'm listening. Yeah. So my screen. Yeah, am I visible again? Sorry.
Yes, you're visible.
Okay. Yeah. Yeah, go ahead. What were your other guards?
If x is odd and y is even, then like we get x, and like similarly, if x is odd and y is even, we get y, and
X, is it
if both
and
are
or
even, we get like minimum of.
minimum? Okay. Yeah. So that's a very good argument. Like it's actually, it works. So I will not do the Haskell code, but I will just say, if x even, comma y odd, then I will give x. If y even, comma x odd, then I will give y. And if both even, then I will give mean of x comma y. And otherwise, pardon my handwriting, I will give any x or y. So let's just say for now, let's have it like this. So yeah, this works, but so this is assuming that y can be odd, but in this folder function, we are first passing an element, minimum element, which is even. Let's see if we can call for this. Yeah. So this is even. So can we have that the minimum element, like we are storing the minimum element in this folder. So shouldn't it be that y is always even? Like, do you understand what I'm saying? Like, so let us
Oh, yeah.
suppose, oh, you do, okay. So yeah, what I'm basically trying to say is that, so initially we have the minimum element to be even, and then we'll update the minimum element only if we have a smaller even element. So the minimum
Just a
element will
question.
always, okay, go ahead.
You're starting with 0. How are we supposed to get a minimum element after that if all the other numbers are positive?
Yeah, so we
Shouldn't
should
you be asking
probably
for
have
the
a guard
maximum?
for that. Yeah, that is a good thing you pointed out. So let's have it, yeah, thank you for pointing that out.
And one more thing, if 0 isn't in the list and you have a list of odd numbers, so then
Yeah.
it will return you a 0, right?
Yeah, that's what it
Exception
said.
that basically odd plus even is odd and even plus even will be.
So suppose equal to mean equal to minus, oh, if I have to do. So if mean equals 0, then suppose we have, like, if the list is empty, we return a -1, and else I print mean, where now we can have that mean is our folder function, for our auxiliary function 0 and ls, and now again we'll have to define the auxiliary function f of x comma y. So what I was suggesting is that since we are always trying to keep y, like y is the value which is being passed on through the folder, so I'm claiming that y will always be even. So this just has to be if, oh wait, I don't have to give it here. Sorry. Yeah. X less than y. Okay, I keep forgetting Haskell syntax. So is it and as a word, or is it just this symbol?
Double ampersand.
Double ampersand.
Okay. And even x equal to x. Otherwise equal to y. So do you guys see why this should work?
These are all positive elements and you're passing a 0 at the beginning. So how is anything going to be less than y in the first place?
Yeah, you're right.
You might want
Okay.
to do a maximum function.
Yeah. Yeah, okay. So there was a lot of mistakes. Thanks. Maximum. Yeah. Does this work? And like, oh, so now we have to have expected one, right? Okay. Oh, wait, yeah. I mean, yeah, okay. Mean isn't a good. Yeah. But we can like have it like auto.
Why did you change that min thing?
Oh, this is just convention because we are trying to find the max elements.
What was min giving a problem somewhere?
Yeah, so as you pointed out, we are passing 0 as the first element. Our minimum element cannot be 0, right? Because what am I like it's a list of positive elements, so 0 will be less than every other element, so that won't help.
Oh yeah.
Yeah. So is the definition clear now? Like, can you see what I'm trying to do with this auxiliary function and how the folder is working? Or do you want me to do it again?
It's clear, I think.
Okay, cool. So we will just do one more example, possibly of folder 1. Arindam, any ideas of a problem which might need folder 1? None of the top of my head, okay, and wait, is something else. So we can take head as min, then traverse the list if anything is less than min, update value of min or something. Yeah, so what you guys were saying is that is actually correct. We were just trying to use folder, so that's that. And
could you just scroll up for 1 second?
Yeah.
I just want to see the. Okay, yeah.
Okay. So no example of that folder 1 is coming to mind immediately. If one of you has a problem or any issue with folder 1 or any other fold functions, I'll just wait 2 minutes if you guys want to type it into chat. Otherwise, we'll be moving into dynamic programming. Okay, 2 minutes is too much. We'll just start at 30. Let's
Could you please go over the type of folder and folder?
The types of folder. Okay, yeah, epic. So, fold R. So what's the idea? Folder will have a function. It will have a start element. And it will have a list. And it will return an element. So now what is the type of function? Function is of the form. It takes A and B and returns C. Now, what is our condition here? Since we want to keep on repeating, our output has to be the same type as the start element, right? Because we want to do f of that again. So whatever the output is, we want to be able to plug it into f again. Am I making sense?
Yep. Yes.
Okay. So yeah. So we would want to have A to B to B, right? Because like firstly, I will be plugging the start element here and then whatever the list element is. And then I will be outputting some element of type B. And then again, we can plug the next element with B and get some element B, right? I hope that is clear. Or is anyone confused with the definition? Wait, am I audible?
Yeah.
Okay, cool. If anyone has any doubt, you can type it in the chat. So the function is of the form, it takes A and B and then outputs a data type of an element of the type B. And then what do we have? We have our start element is of type B, right? Because our first operation will have B here. So start element will have to have type B. And since the function spits out a value of type B, our final element will also be of type B. And what is left is this element A, which we are getting from list. So what will this be? This will be containing elements of type A. So let us write down folder. Okay. So firstly, it has a function. It goes from A to B to B. Then we have the start element, which is of type B. Then we have our list, which is of type A. And finally, we have our output, which is of type B. Does this make sense?
Yeah.
Okay, okay. Let's do fold L also. So fold L. So fold L will also have a function start element, a list, and it will output some element at the end. Very cool. So again, our function is something of the type f of A goes to B goes to C. Suppose our start is of type B. List is okay. Let's start is of type A. Our list is of type B. And our final element will be of type B. So, yeah. Okay. So again, with this function, what do we need? So our first element will have to have the same type as start. So this is A. The next element will have to have same type as the list. So this will be B. And our output will again, since it will be plugged into f of A and next element of the list. So our output will have to be the same type as start. So that will be A. And this will mean that start A and yeah. So our final element will be something of f A comma B, which will also be of type A. So the definition of folder will be folder A to B to A, and we have a start element A. Then we have a list of type B, and then we have our output of type A. Is this clear?
Most of the times we had B to be the same type as A. So I don't know, like if we could have B to be.
Oh, okay. So yeah, one example is sir covered this. It's the identity function. So fold L of colon and the empty list and ls. So what this does, so what does colon do? The type of colon is colon takes an element and this thing, and it outputs element, right?
Yeah. Yeah.
Okay, wait. Maybe not folder. Let's do folder. That will be better. Okay. Yeah. So here, see, one of the elements is of type single. So okay. So let's just define. It's of the form A. Okay, so first, do you guys understand why this is the identity function? I think sir did it in class. If you want me to explain it again, I can do it. Does anyone have any doubt with this?
How is it identity? Like we are taking two different arguments and we are returning a single
Okay, yeah.
single value.
So yeah, let's see this. Okay. So suppose let's take an example. Folder of this thing, and then we have this, and suppose our list is 1, 2, 3. Let's just keep it short for now. So what will our first operation be? Our first operation will be colon of the first is the element from the list. So that will be 3 and our empty list. So we already know what 3 is to empty list is. It's basically equal to this thing, right? Does this time make sense?
Yeah.
Okay, epic. So let's do the next iteration. Next will be 2, and our new output is 3. So this is basically 2:3, which is the list 2,3, right?
Yeah.
Okay, epic. So finally, 1 and then 2,3, which is 1 is 2, 3, equal to 1, 2, 3, which is basically this list itself. So it's the identity. Like, did you understand the working?
Yeah.
Okay. So let us define the type of folder for this, like specifically. So, okay, so this is actually bad notation. Folder shouldn't be like this, but yeah, sure. So our first is this operation. So what does this operation do? It takes an integer. Oh wait, why am I putting? Yeah. So this is actually like, it should be universal, but we are just doing this for this particular case. So it takes an integer and a list of integers, int, and it spits out another list of integers. Does that make sense? The type of colon?
Yeah.
Okay, very good. And then next we have our first argument. So that will be a list of integers. And okay, this might be a little confusing because like the next argument is also a list of integers, but here it's like, it's meant to be like a list of the data of this type. And this is basically analogous to this type. But whatever, yeah. So next is the list of elements, which is this ls. And it will again spit out an element of this type. Of type int. So this probably, we can have more complicated examples, but this is a simple example to see that like, it's not always that A is to A is to A. It can be different types also. So here, yeah, so folder of this, and our definition of folder, I'm sure I can copy this. Okay. And then I control C. And I can robot. Yeah. Okay. So our definition, let's just check whether this is consistent. So our A, wait, I can wait a minute. Okay. Yeah. So, this is weird. I messed up something with over. Yeah, wait. I'll just reset one. Yeah. Can we try to? Yeah, epic. So yeah. First is int, which is our type A. Then is list of int, which is our type B. Then is list of int, which is again type B. That's fine. And then we have this int, which matches with type B. Then we have a list of integers. So A is type int. So this also matches with this. And finally, we have B, which is also a list of integers. So it does match. This is probably complicated, but like, was I able to sort of get it across to you what this means?
In the previous folder column, we are like, as a result, we got the list 1, 2, 3 itself. So
yeah,
like the type B is matching the type A. Like its list at the end.
Oh, okay. So see, yeah. So what you're saying is here we have A equal to B, but like a simple example where that's not the case is just the plus. So order of plus comma 0 comma ls. Then our what? Then B is int and A is also int. So our output will be int. And then our output will just be same type as B and not this thing mod like list of A is equal.
Yeah. Already.
Cool. So does anyone have any other doubts with folder or folder? Will I wait again? Or do I just move on? Okay, so I assume no one has any more doubts with folder. So let's move on to. Okay, wait. Right. Let's just keep it first. Down. Okay. So yeah, many of you told us that you are having difficulties with dynamic programming. So we first want to clarify whether you are having an issue with understanding the concept of dynamic programming or how to use dynamic programming in Haskell. So can one of you help me out here?
How to use dynamic programming in Haskell.
Okay, so like why we do dynamic programming and stuff, that is more or less clear to you.
No, not for me. Can you start from the beginning?
Okay, yeah, sure. So yeah, what we have done so far is we have done recursion, right? So a simple form of recursion is f of n equal to suppose some I don't know some g of n, a function of n, plus f of n minus 1. Where we are using the values of, wait, why am I writing quite? I'll just like this one. Quite.
So I understand the doubt. I mean,
Yeah, go ahead.
I necessarily to write everything in syntax, but don't know the syntax can be written algorithmic form or
Wait, your voice is cutting out. Can you repeat once more?
is it mandatory to write always the syntax? I mean, syntactic sugar should be always correct. Or if you don't know the syntax, can you write the pseudo code or some kind of algorithm? Will that work?
Oh, so I think, sir, usually it's that write a function which does this. So unless sir mentions otherwise, it's usually like you can normally write pseudocode, but if sir says that write a function which does this, then you'll have to write Haskell code only.
For a recursion, we could write, if I don't know the syntax, can I just write the function, recursive function?
Yeah, like you can write a recursive function. Suppose sir said that write a function in for doing some task and you give him a recursive relation. You will definitely get part marks, but I can't guarantee full marks if he said that write a function because he might have intended you to write it in Haskell.
I see.
Yeah. Okay, cool. So let's start with the example, sir. Too. So Fibonacci of n is Fibonacci of n minus 1 plus Fibonacci of n minus 2. So yeah. So let's do Fibonacci of 3. Instead 3. So what do we first need? I need Fibonacci of 2 and I need Fibonacci of 1. Now I know the Fibonacci of 1 is 1, so that's cool. And then for calculating Fibonacci of 2, I want Fibonacci of 1 and Fibonacci of 0. This is equal to 1 and this is equal to 0. So what am I, so see, here I am calling Fibonacci of 1 twice, right? So what that means is essentially like we have already calculated the value of Fibonacci of 1 here. So we shouldn't be calculating the value of Fibonacci 1 here again. Probably, okay, so maybe let's wait for Fibonacci of 4. So that will be a better example. So this will be Fibonacci of 2. So Fibonacci of 3. So we have put 0. I put 1. F of 1. And this will be F of 1. F of 0. Yeah, so as you can see here, like when we are calculating Fibonacci of 4, calculating Fibonacci of 2, but like that is actually a redundant computation because we already know the value of Fibonacci of 2. So why will we compute Fibonacci 2 again while we are doing Fibonacci of 3? So this is where dynamic programming comes in, where you basically don't want to repeat computations. So once you've computed the value of Fibonacci of 2, you want to store it so that you can you do not require to if you require to use it again, you will not have to compute it using the recursive relation. Am I making sense?
One second. Could you repeat it?
Sorry, your voice was a little muffled. Can you repeat?
Yeah, it is muffled. Can you repeat once again? I lost you there.
Oh, yeah, sure. So, yeah, okay, let's draw the Fibonacci table for 4 again. So, I'll just be writing F because it's shorter. So, Fibonacci of 4. So, our definition is Fibonacci of n minus 1 plus Fibonacci of n minus 2. So, for calculating Fibonacci 4, we call Fibonacci of n minus 1. So, that is Fibonacci of 3. So, for calculating Fibonacci 3, I will first call Fibonacci of 2. And then for calculating Fibonacci of 2, I will be calling Fibonacci of 1. This returns 1. And then I want plus Fibonacci of n minus 2. So that's Fibonacci of 0. This returns 0. So I get this to be equal to 1. And then for calculating Fibonacci of 3, I will call next f of 1, which will again return equal to 1. This will be equal to 2. So far, is it clear? Like this recursion tree that I've drawn?
Yeah.
Okay, epic. So what the other part will be is now we want to call Fibonacci of 2. And what will Fibonacci of 2 do? Fibonacci 2 will first call Fibonacci of 1. This will return 1. And then it will call Fibonacci of 0, which will return 0. And then I'm getting 1 here. And so Fibonacci of 4, I can get to be equal to 3. So what we are not happy with is the fact that I already computed Fibonacci of 2 here, right? And yet we are again computing Fibonacci of 2 here. Like it's the same computation, but we are doing it twice. So this is where like recursion, it has to do a lot of computation, but a lot of it is redundant. So this is why we want dynamic programming. So what dynamic programming? I think I needed programming. Okay, yeah, this is the sheet. Yeah. Programming will do is once you have calculated f of 2, you would store the value of f of 2 so that when the next time I call f of 2, so first suppose I call it here. So let us instead think of it this way. So we have a table for the Fibonacci numbers. There is the Fibonacci of 0. There's the Fibonacci of 1. There's the Fibonacci of 2. There's the Fibonacci of 3. And there's the Fibonacci of 4. So we first have set Fibonacci of 0 to be 0 and Fibonacci of 1 to be 1. And now suppose I'm calling Fibonacci of 4. So Fibonacci of 4 will first go to Fibonacci of 3. Fibonacci of 3 will go to Fibonacci of 2. And Fibonacci of 2 will compute to be equal to 0 plus 1, and it is 1. Very cool. And then Fibonacci of 3 will also call Fibonacci of 1, which is 1. And then 1 plus 1, it will set it to 2. And next time, I've gone from Fibonacci of 4 to Fibonacci of 2. So now, instead of like when I go to Fibonacci of 2, I see that I have already computed Fibonacci of 2. So instead of again calling Fibonacci 1, Fibonacci 0, and then adding it up, I'll just put in the value of Fibonacci of 2 that I already have. So that's 1 plus 2, and I'll be setting it to 3. So is it?
We are giving a recursive definition of the function, right? We're just, I mean, essentially, we're just giving a recursive definition of the function, right? I mean, f of n is equal to f of n. I mean, inductive definition.
So yes, so that's the definition of the function is, yeah, what you said.
F of n would be f of n minus 1 plus f of n minus 2. I mean, we have to prove it for.
No, there's nothing to prove. So this is the definition, and we also said that f of 1 equal to 1. Wait, can you repeat?
This is also inductive.
Yeah, it's inductive, absolutely. So, like in recursion, there is no problem with correctness. Like as long as your code is fine, your recursive relation, it should be fine. It will be computing things fine. What we want to do is, even while computing, we don't want to do the same computation multiple times. So this definition is absolutely correct. What I don't want to do is, I don't want to calculate f of 2 or for higher values, f of n minus. So see, what basically happens is when I want to compute f of n minus 1, what I need are values of f of n minus 2 and f of n minus 3, right? So now next time when I'm adding f of n minus 2, I have already computed the value of f of n minus 2 for this part, the f of n minus 1 part. So instead of again computing f of n minus 2, what I want to be able to do is to reuse this value, which we already computed.
Okay.
Am I making sense?
Yeah, yes, sir.
Okay. Is everyone more or less clear with this? Like why we want to do dynamic programming? Is there anything that's chat? Okay, there's not. Okay, I'll assume everyone more or less understands why we want to do dynamic programming. Okay, so now how to do dynamic programming? So with Fibonacci numbers, it's actually, there's a pretty easy way to go about it. So fib of n equal to, we define this helper function, go of 0, 1 and n, where go of cannot be 0 equal to 3. Otherwise, go of a, b and n is equal to no plus 2 minus 1. So what we are doing, sorry. Yeah. So what we are trying to do here is, yeah. So we'll start with the pair 0, 1, which is Fibonacci of 0 and Fibonacci of 1. And suppose I want the 5th Fibonacci number, right? So we will go to the next iteration. So what is that? That's b and a plus b. So that will be 1 and 1. And these are, okay, so this is 0 and this Fibonacci of 1 and 2. And now we are at 4. And then we will go to 1 and 2, I believe. So that's 2, 3. And we are at Fibonacci of 3. And then we will go to 2 and 3. I think this is 4. This is 2. And then we will go to 3 and 5. Is this 4? This 5. And I have 1. Finally, we will go to 5, 8. This is 5. So 6 and 0. And here I've reached this terminal case and I will return 5. Okay. So firstly, see here that every Fibonacci number is only being computed once. Right. So the first, okay, maybe, yeah, it's actually being computed once. So firstly, I have the 0th Fibonacci number, which I'm passing. So that's that. And then the first Fibonacci number, which I'm passing. So that's 1. So these are being computed only once. And then the second Fibonacci number, 1. So that's just one operation. And that is giving me this value. So that was one computation to calculate the second Fibonacci number. Very cool. And wait, do people understand this?
So what makes this dynamic per se? I mean, this is what we
Okay.
do if you are trying to use loops, right, instead of Haskell. So
This is, yeah, exactly. This is what you would be doing if you wanted to use loops. Yeah. So, okay. So in that case, yeah. So when you're using loops, what you're doing is you're essentially keeping track of Fibonacci of n-1 and Fibonacci of n-2, right? And then you're doing Fibonacci of n-1, you're updating it to the Fibonacci of n-2, you're setting it to that of n-1, and then you're calculating n as n-1 plus n-2, right?
yeah.
Yeah. So in a loop, essentially that is dynamic programming because every Fibonacci number is being computed once. So Fibonacci numbers are actually like a simpler form of dynamic programming where you don't need to go into like you don't need to store the complete table of Fibonacci numbers because to compute the next Fibonacci number, you only need the one before. So how about we go with a different example of Fibonacci? Like suppose we have a function f of 1 is equal to 1 and suppose f of n is equal to f of n-1 plus dot dot dot. Okay, let's just keep on plus f of n-2 plus f of 1. Okay, suppose we are given this function and we want to calculate the nth value of this function. And what you could again do is do the recursion, like you can just simply call the recursive call, but then again f of 1 n-1 is calculating f of n-2 by its recurrence relation, and then all these subsequent calls will already have been computed and so they will be essentially redundant. Do you see why?
Yeah, I think so.
Wait, did you repeat? I couldn't hear you properly.
Yes. Yeah.
Oh, okay. Very cool. Does everyone else like, okay, no, this is actually not even a problem. So we'll first, okay, yeah. So we kind of demonstrated how you would do the dynamic programming for Fibonacci numbers. So would anyone like, not Haskell, just would anyone like to say how you might do dynamic programming for this problem? Like, don't need to think in terms of Haskell code or anything. Just give me pseudocode or an algorithm or any idea of how you might do dynamic programming for this.
Make a list and like add the values every time.
Epic. Yeah. So what we can do is we have f of 1 equal to 1. And then I think this is what you're suggesting. We compute f of 2 as equal to f of 1. So, and then we calculate f of 3 and dot, dot, dot. We keep doing so until we have computed f of n. Is this what you're saying?
Yeah.
Okay. Yeah. So that's exactly what you would want to do with dynamic programming, because in here, like you're computing each f of n exactly once. And then what would my f of, so suppose this table is dp. So then I'm setting dp1 equal to 1. And then suppose I run a loop for I equal to 1, not 1. M dp of I equal to 1 n minus 1. Does this make sense? Okay.
Yes.
Unto I minus 1, right?
Yeah. Okay. Thank you. Okay, so this is the concept of dynamic programming. So let's do another example of how you would do dynamic programming, and then we can move on to implementing it in Haskell, which is an entirely different method. So let's cover the problem of the longest common subsequence, which studied in class. Actually, no. Since we did that in class, we'll not do that. Let's do edit distance. Edit distance. So suppose given a string, you can do
Hi, Diptaksho.
Yeah.
I just wanted to ask whether Sir did this flowchart in class. I
Okay.
think it was a little confusing. So if you could explain that, that would be really nice.
Which flowchart? Let's just
Not this one. That was in. It's like the lecture before this for Fib.
It was, let's see. So do you mean this
Yeah,
thing?
yeah, this one, yeah.
Yeah, this one is actually okay. So this is actually okay. Yeah, I remember this. We'll get to it when we're discussing the code for Haskell, because Haskell syntax of dynamic programming is an entirely different matter. I don't want to confuse
Okay.
that with how dynamic programming works. We'll cover that, but just remind me if I forget.
Sure.
Yeah. Okay. So yeah, edit distance given a string, you can do the following operations.
So
One
in
is
the previous problem, can't we do it in even shorter complexity?
Yeah, go ahead. Huh?
By just putting the second element as 1 and then doubling every other element as the previous element, because we are just adding the same thing that was before.
You're probably right. And if it's 3 would be to then with 1. I'll just have to think about it. So you're saying that f of n, you could do f of n minus 1?
Yes. From n equal to 3.
Okay, so let's see if that works. So f of n minus 1 plus this thing. And what's f of n minus? Okay, no. If I want to prove this inductively, how would I do it?
F of n minus
Okay,
2
yeah,
is,
right. So this is plus f of n minus 1. Okay, yeah, that's cool. Yeah, so yeah, that would actually be a very smooth technique. And then you can actually go even further, because then I can simplify these two. So I can do 2 to the power probably n times f of 1 or something like that. So yeah, this is mathematical simplification. So you can always use maths to simplify your function to get it in even O1 time. Here you don't even have to compute, like do a loop of length n. So yeah, this was not a very good choice of a function, but I was just trying to demonstrate how you would do that in dynamic programming. This is, yeah, you can do it recursively or like just on value of f n minus 1, or even purely you can find closed form for it. Someone has something in the chat. If you have a problem with that flowchart, then I will make some annotation from that and listen. Let me show you. Okay, yeah, sure. We'll get to that. Given a string, you can do the following operations. Yeah. Add character and position. I don't know. Position. Remove a character from any position. Or 3. Replace a character at any position with some other character. Okay. So maybe something like, let's take the example of smitten. Suppose I want to add the character A in the 4th position. Oh wait, this is perfect. Yeah. Okay. So plus A at suppose 4th position equal to, I will get SMIP AENs meta 10 here. Okay, and suppose I want to delete the character in the third position, -3. Oh. Wait. Okay. So that would be SMPTEN. Yeah, and suppose I want to do a smitten. I have no notation for this. Let's use this. And I want to change the character in the fourth position to D. So that would be smitten. Yeah. Okay. So are the operations clear? Okay.
Yes.
Okay, cool. So let's next what we can ask is given string AS comma BS, what would be the minimum number of operations to convert AS to BS? Okay.
Shouldn't it be semi-10 in the first case when you added A to fourth position?
What? So you're saying that it will be SNIAT 10?
Yeah.
Yeah, sure. That's notation. Yeah. Yeah. Okay. SNIAT 10. So this is your problem. So we will do it step by step. First, we want to. Okay. So how would you even solve this problem? Does anyone have any idea? Does anyone want to try? I will show you the operation button.
First, we need the length of both of these strings, I think.
Okay, very cool. So n equal to length of AS and m equal to length of BS. Okay, next.
Then, like, if n is greater than m, we need to look for that.
Okay,
Actually,
so
having the longest common subsequence would also help.
yeah, how would having the longest common subsequence help?
Because the elements in the longest common subsequence are ones which you don't need to touch. So then you would be breaking it into smaller lists, strings, which you can change.
Yeah, that is correct. But that would be okay if you couldn't replace elements. But replacing elements actually, like you can get a much longer subsequence. Okay, I'm not actually sure. There is actually a counter example as to why the longest common subsequence probably doesn't work. Arindam, do you know counter examples or if this is correct?
Counter example to what?
Would longest common subsequence work? The computing longest common subsequence and then subtracting that from the difference in lengths?
No, not for the difference in lengths. We have to find the minimum number of operations to convert it, right? So
okay, yeah. So the longest common subsequence wouldn't have to change, and then maybe
we just have to change the other elements.
Yeah, we just change them. Yeah. So Arindam, does that work? Like, it is an idea. I'm not sure it is the correct idea. Yeah, like your idea makes
even if it works, anyway, you will have to do some sort of DP.
Yeah, you will still have to do some recursion. So there's that, but Yeah, so let us try it without longest common substring. I'm not saying that your solution is wrong. It's probably correct. Like I don't exactly remember, but there might be some example where it doesn't work. I'll try to think of it, and if I can, I'll let you know shortly, or maybe after the tutorial if I can remember one. But yeah, so that was one approach. Can one of you try, or same person try a different approach?
Probably the simplest thing to do would be like exchange like every element of AS to the corresponding element of BS and append or like delete, or if depending on the length.
So like you want to like compare the first two elements. If they are not equal, what do you want to do? You want to delete the first element of A, or you want to replace
No, I
it, or you
just
want
want
to
to
insert
keep
something before?
replacing it. Yeah.
Oh, so you want to replace. So how are you sure that always replacing will work? Sometimes maybe inserting is a, so yeah, let's take it. So what you're saying is suppose AS equal to okay, and then BS equal to ATA. And then if you're comparing the first two elements, you would say that I would want to replace the first element of AS with A. So I'll get AATA. And then when I compare the next two elements, I get an A here and a T here. So I would want to convert that to T. So I'll get an ATTA. Then the next two elements I would compare and see one is T, one is A. So I would want to convert it to ATAA. And finally, I'll see that this has more length. So I will make it ATA. So this is 4 operations, but yeah, it's an algorithm to compute one way to get the thing, but a much simpler thing would be just delete B. Right. If I delete B, then I'm already getting equal to yes. So this is 4 operations and this is 1 operation. Does that make sense?
Yeah.
Okay, cool. So, but you're on the right track. So would you like to try it, Kumar?
I'm sorry, what?
Like you're on the right track. It's you have to compare the first elements and then do something. But would you like to like rework on what that something would be?
Yeah, probably if the second string existed as a subsequence of the first string, you can delete every other element of that.
Yeah. So that's again going back to the longest common subsequence problem. We decided that
no,
since like your first approach was comparing the first two elements, so something along those lines. So let's do okay, so first is what if A0 is equal to B0? What then?
and then leave it as it is.
Absolutely. Then dist equal to dist of okay, so we can just call it tail of AS comma tail of BS, right? Because the first elements match.
Yeah.
Okay, very good. And what do we do otherwise?
Yeah, you can probably go on till if they're not equal, delete it, and as long as it happens, and in the end append the rest of B's.
Okay, so that would be that if they're not equal, I will delete it. So wait, let me try to think of an example.
We can
Okay,
delete
so
or replace and take the minimum, whichever.
Yeah, so yeah, I'll just give him his counter example and then we'll get on with what you're saying. So suppose we have AS is BPA and BS is ABTA, and then what your algorithm would do is it doesn't first match, so it will delete the B, and then it will compare TA and ABTA, so that won't match, so it will delete the T, and then it will compare A with ABTA, that will match, so it will keep the A, and then it will add 3 more elements, so that will be a total of, I believe, 3 plus 3 equal to 6 operations, but our minimum would just be an insert and A, right?
Yeah. Okay, so
Okay,
then
so
you can insert the first element and then continue.
yeah, exactly. So I think someone else was suggesting something like this. So whoever that was, can you go again?
We can delete or we can replace the first element, and then we can take whichever one takes minimum number of steps.
Okay, so we can delete or replace. Why can't we insert? Because in this case, inserting would be the best, right? Because suppose I
Alright, we can
replace B
also
with A. So yeah, or insert. Very cool. So what would deleting do? Deleting would mean I am deleting the first element of AS. So I would want the distance between the tail of AS, which is what I have now, and then I would want to match it with BS, right? Does this make sense?
Yeah.
Okay, very cool. And what would replace do? Replace would set this to be equal. So suppose I replace the first elements to be equal, like first element of A to be equal to that of B. And then what could I want?
Tail is tail BS.
Absolutely. Does everyone see why this will be tail AS, tail BS, or do you want me to go over it? Wait. Oh dear. Yes. Does anyone have any doubt with this? Okay, I'll assume no one does. So what would you do if you... Oh, yeah, go ahead.
So the LCS idea, what was the LCS idea? First you find the LCS, then?
Yeah, whoever was suggesting, can you say that? Wait. So whoever gave the LCS idea, can you just elaborate on what we're trying to do for the longest count subsequence? Or maybe you can just message or in them in the chat, because then like other people won't be confused. Yeah. So yeah, while he's doing that, would anyone like to cover how you would do the distance for inserting? So insert would mean that I would insert an A here, and then I would want to match the rest. So how would that work?
Same as the replace.
Okay, no, it's not the same as the replace, because
List of
so
AS tail BS.
yeah, absolutely. Oh wait, just a second. I want to know these marks. Yeah. So like someone said, I'm adding an element before AS, so I still want to match the all of AS with the tail of BS. So it will be AS, comma tail of BS. And then I will add a +1 because I have done one edit, one operation, right? Because it's either I'm deleting or replacing or inserting. So 1 plus whatever is the minimum of these values. So does this recurrence relation make sense? I can repeat because it might be complicated for some if anyone is having an issue.
Yeah, could you repeat?
Yeah, sure. Okay, so firstly, what we are trying to do is we are trying to solve this problem recursively. So yeah. So firstly, we are checking the first two letters. Suppose AS0 is equal to that of BS0. Then everything is good. We can just skip these two elements and we can check the minimum distance from the rest of AS to the rest of BS. Does this make sense?
Could you repeat distance? Because I think I lost network at that time.
Oh, okay. Yeah. So no, distance is basically its notation. So distance between two strings, suppose x comma y, equal to min operations to go from X to Y.
Okay. Yeah.
So we basically want to calculate the distance between AS and BS.
Yeah, okay.
Okay, very cool. So let's go again. AS of 0 is equal to BS of 0. So then we have our first letters have matched, and we want to match the rest of the string. So what do we do here?
I mean, you check the rest, right? You leave these two and you...
Absolutely. So it's just distance between the tail of AS and the tail of BS, right?
Yeah.
Okay. So suppose not. Then I will have to make at least one edit to make the first character of AS equal to that of BS, right?
Yeah. Yeah.
Okay. So first what we can do is, let's match the order we were doing here. So, okay. So first we can do is, delete first element of AS, in which case, so that is one operation plus, and now what do I want to match after deleting the first element of AS?
Tail of AS and BS.
Absolutely. Tail of AS and BS. Number 2 is, suppose we replace first element of AS. So what does that do? So AS, I'm setting AS 0 equal to BS 0. So that is one edit plus what will be the distance now?
I mean, you want to check again, don't you want to check tail AS and BS?
Yeah, exactly. So it will be just tail of AS, comma tail of BS, because both their first elements now match.
Oh yeah, tail of BS, yeah, sorry.
Okay, epic. And then the final is, I want to insert before first element of AS. So that is one edit plus what do I want to do now?
I'm sorry, for replace, what did you do? You
Oh, okay. So suppose we had some A, B, C, dot, 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 dot.
Yeah.
And suppose here we have a B, C, C, dot, 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 dot. Okay. So firstly, we're comparing these two and I'm seeing that they're not equal. So I want to replace this A with a B. Okay. So once I have done this, the next thing I want to do is I want to calculate the minimum distance between these subsequences, like these substrings.
No, I mean, how do you judge between replace and insert? I mean, in the sense you have, okay, you like here you can easily see you want to replace A with B, so you get.
Oh, yeah. So we can't actually judge what will be the best choice at any position. So we are just going to calculate the best choice, like all the possible choices, and find from their values, we will calculate the best choice.
Okay.
Yeah. So right now we are not concerning ourselves with what will be the best course of action. We just want to calculate the courses of action. So
Yeah.
like, does what we are doing with replace make sense?
Yeah.
Okay, very good. So what would you do with insert?
Again,
so insert would be insert BS of 0 before AS.
I'm not sure. Tail, yes.
Okay, no. So yeah, what I'm doing is, so suppose I have this string AS and I add BS 0 here before it. Okay, and then below it I have all of BS. So now what? Our first elements match, and I want to match the rest of the strings, like this thing and this thing.
Oh,
right?
Yeah.
So what will it be?
AS and I mean, like, how do I say BS minus tail
Yeah, so
BS?
tail. Absolutely. Does everyone else see why this works? Like, we are just computing the values. We are not doing the minimum or anything. Does anyone have any issue with this? Okay, I'll assume no one has any problems. And then finally, so we have tried matching the first elements by deletion, by replacement, and by inserting. So finally, what we want to do is we want to take the best course of action. So that will just, it will be the minimum of the distance if I delete, the distance if I replace, and the distance if I insert. So does the recursive definition make sense for everyone?
It will be 1 plus the minimum, right?
Yeah, we've already put a 1 plus. So does this mean?
When we are comparing the first element, we are doing an operation. So shouldn't it be 1 plus?
No, comparing is no. So like if the first two elements are equal, then we don't want to change them. So I don't want to do any operation on them. So I just want to match the rest, like the remaining parts. So again, let's go back to a question. So the operations are, I can add a character at any position, I can remove a character from any position, or I can replace a character at some position with some other character.
Oh, okay.
So can you, okay,
Yeah.
you understand? Okay, very good. So this would be our recursive relation, and that's very cool. So okay. So okay, this is a recursive relation. So again, recursion means we will have multiple calculations, like we have to do the same calculation multiple times. So let me just take an example of that times. Okay, like, do I give an example? Like, is it like how do I do it? Okay, so let's just set AS equal to Smitten and AS equal to sitting. And what you want to do then is, so our recursion will first be, so S is matching with S. So, okay, so what do I do? Okay, no, this will take too much time if I write it at each step. I'll just be explaining it already. So S is matching with S. So I will want to calculate the distance between mitten and itting. So, oh wait. Am I audible?
Yes.
Oh, okay, good. Yeah, so I will be wanting to match mitten with itting. So first I see that M and I are not same. So I can either match itten with itting, or I can match, what were the options? Yeah, so I can match imitten with itting, or what's the other option? To replace, or I can match itten with itting. And then, so next I would have T and T same. So I would be wanting to match En with, I think, ing. And here, what I have the very next characteristic. So I would match mitten with TT ing, or what? Yeah. And then here I have itten TT ing. And see, so here's the funny thing. So suppose I want to try a deletion here. So that would mean I want to compute the distance between itten and TT ing, right? Am I making sense? So like first what we did was we inserted an I before mitten. So that was emitten and itten. Now we want to calculate the distance between these. So again, the first two are same. So we'll move on to the next. So that will be mitten and tting. So m and t are different. So what we can do is we can try removing m, right? So that will give me the have asked me to compute the distance between itten and tting. Does that make sense?
Yeah.
Okay, very cool. And also, suppose we did replacement. So suppose I replaced the m with I, and then I had II10 and itting, and then again the first two matched. So I will again be wanting to compare itten with tting. So as you can see with recursion, we are having to do the same computation twice, right? Or maybe it can be even more than once, like later points. So again, we want to introduce DP because the same operation is being done multiple times. So let's see why the same operation is happening multiple times.
Yeah.
Okay. Yeah. So now would anyone like to attempt how to do the dynamic programming of this? Since we've already gotten this and you sort of did something similar for longest common subsequence. So yeah, as I recall, I think what we have defined is the function g, and then there's an a and a b and a ul, and then we did all that stuff where we compared this thing. So whatever, yeah, let's not worry about that now. Would anyone like to attempt how, like, try to do, just try to attempt the dynamic programming version of this? I'll just copy the recursion relation. Okay, sure. Yeah, no, I'll just keep it here so that you can see.
I think I get the idea of how to take a lot of time for me. But the idea is we'll want to build a sort of table of these values.
Absolutely.
And what these three things are representing is going up, left, and diagonally on the in the table. And so once we build this table, we will just move up and down the table to find the up and left the table to find the answer that we want.
Absolutely, what you said makes sense. So suppose I think this was m, and this is n. So at the first stage, we are matching the first two, and if they are not equal, I want to do, okay, so yeah, suppose this table is called D, okay, and this is the I, like the row, so like dp I comma j is the jth column, ith row, and it stores the distance between which so yeah, okay, I think it should be take I of as and spelling, take j of bs. So does the definition make sense?
Yes.
Okay, very good. And then we will just be using our recursive relation. So let us assume, yeah, so dp I comma j is equal to if as of I, this is basically the, does sirs call it bang? Yeah, bang, bang. Yeah, so this is basically same as as bang, bang I, equal to bs j, then I just want the dp of I minus 1 yeah, j minus 1, because our ith and jth elements match. So I just want to match the remaining elements. And otherwise, exactly analogous to what we did here, I want 1 plus minimum of where let's just, would anyone like to tell me what these DPs correspond to? Like what operation is signified with DP I minus 1j?
Remove.
DP I minus 1j is remove, absolutely. What's this?
Interchange.
DP I minus 1j. Replace. Wait, I think my internet sort of cut out. Can you repeat what you were saying? Wait, am I audible?
Yeah, I think that was just feedback.
Oh, okay, cool. Yeah, and what will be DPI j minus 1?
Insert.
Add, insert.
Absolutely. Does everyone see why this is the case? Because this is like the most important part of dynamic programming. Like maybe not dynamic programming, that's awful presumptuous. Like of this problem, this is the most important part. Why these signifies these operations? So if anyone has any doubt, you can let me know. Because after this, we'll be moving on to the Haskell syntax for this stuff. Okay, then I'll assume no one has a doubt. Cool. So then what was this problem of the edit distance clear?
Could you just scroll up 1 second? Just a second. I just want to see.
Yeah. This part or the recursion?
Yeah, 1 second. No, a little below.
Oh.
Little down. Yeah, 1 second. Yeah. Okay. No, it's done. I looked at it.
Okay, cool. Then is it clear?
Yeah.
Okay. I assume it's clear for at least most. If anyone still has any doubts, you can let me know via WhatsApp or anything. We'll then move on to the Haskell implementation. And yeah, first thing we wanted to do is this weird list thing. Okay. So what was the list thing that sir gave? Fib equal to colon fibs. Okay, so this is basically the nth element of fibs. That's fine. So yeah, we want to calculate fibs, right? So fibs. Okay, type this instead. Okay, no, let's not. Equal to 0 is to 1 is to z. And what do I have? Z equal to 1 is to go. 1 is to z. 1 is to, yeah. Where go this. Okay, then sir do the flow chart thing. Okay, yeah. So I am assuming this is okay. Let's just say it from one. Yeah, let's suppose it's the correct one. Okay, so the first element of Z is a 1, and then yeah, so this is the operation colon. So, oh shit. What? I'll just skip at this because I'm terrible at running cycles. Yeah, so 1, and then there's colon here, and colon will take another list, which is go of 1:z, comma z. And then what is the first element of 1:z, comma z? So that's, here is a 1. And then the first element of z is also a 1 because we set it here. So that will give me a 2, right? Does that make sense?
So for z, it's going to again recalculate z, right?
Yeah, so that's the thing about Haskell's Recursive Relation. It's not super intuitive. Like we already have defined the first element of z. So while accessing z, because of the lazy evaluation of Haskell, since it only is the first element of z, it can actually deal with like a self-dependent definition of itself. So I can actually do 1:z. So like this will be 1, and then z, we have already defined the first element of z to be 1. So I can actually do this go business here because I have the first elements of both.
I think what I'm trying to say is when it passes z to go, it's going to be sort of the same instance of z that was previously defined, or it's going to.
Yeah, absolutely.
Okay, I'm not sure if I know what I'm asking. So never mind. That's
yeah. So here basically what it means is it's 1:go 1:z, comma z here, right? This thing, because I've passed z. That's what I'm trying to say, right?
Yeah, probably. Yeah.
Okay, cool. So again, see, and then go, the first thing is 1:z. So this is 1. So right now we only need to concern ourselves with x and y. So x plus y will give me a 2, right? And then we will do go on the remaining thing. Okay.
Yeah.
Okay, very cool. So that will yield 1 colon, and then the first element of go, we compute it to be 1 plus 1 equal to 2. Okay, no, let's not do that because there will be an operation again. Oh, so here we want to put this value. So let's first put the colon, and then x plus y, we got it to be 2. And now we want to calculate go of, what's that? Yeah. So z, and then we want tail of z, right? Because it was 1:z and z, so we removed the first element. So it's now z and tail of z. Does that make sense?
Could you repeat that one time? As in why? I didn't get why what that colon exactly is representing here and why we're putting it there.
So we are basically, so suppose we have an equation of the form. Oh boy, yeah. Yeah. So suppose we have A is to B, where so what? A is an element and B is a list of elements, right?
No, right. What I meant is I didn't get why we're putting it over there in the flowchart.
Wait, like why we are representing it in this way?
No, as in, so the second colon is there, right?
Oh, the second colon. Yeah. So basically, this is the expression that
we put one colon and then another colon. I didn't fully get why we're doing that. Yeah.
Oh, like why we're joining these colons. That's your point?
Yeah, why we're joining them and how I should be interpreting this in terms of what the compiler is doing.
Yeah, absolutely. So what the compiler is doing is it's doing 1:go of 1:z, comma z. And what this is evaluating to is 2:go of z, comma tail of z, right?
Okay, so now we get 1:2 go of z, comma tail z.
Absolutely, yeah. This is just research notation. Like it's not super important. And then what we can do next.
Then,
so yeah. So
thank you.
Yeah, no problem. And then we have go of z and tail z. So first element of z is 1, tail z, second element of z. So that would be 2. So we have 1 plus 2, that is 3, is to go z, and then we have tail of tail of Z, and then this will keep on continuing. So does the flowchart kind of make sense now? I'll just go back.
Yeah.
To
It makes sense now. Also, would it be tails? Just the tails. Like.
Wait. Which one? Oh yeah. This could be tails.
Yeah, the flowchart makes sense now. Thank you.
Okay, cool. So that's one thing, and I think most of you probably would have had an issue with the syntax of LCS, right? That's not a good way to put it. Like, I think.
Before we get there, can I just ask why we redefined fibs in terms of Z? I mean, what was the issue with the previous solution that we had? I mean, when we did the Fibonacci number, using
I'll just go back to your previous solution. So this thing, you're saying that why we redefined it with that Z business?
Yeah, exactly.
So yeah,
I mean,
that's just yeah. The solution was correct and stuff. So I just wanted to give more intuition. Like zip with plus fibs and tail fibs is probably less. Like it's just for intuition. Like there is no purpose to doing it that way. So I think so. I just wanted to give you intuition for how how this zip with plus and fibs of tail fibs work. So that's why he defined it this way so that it was clearer.
Oh, okay.
Yeah. That's the question. Like the first thing is perfectly correct, and there is no computational problem with taking it. Okay, so
Sorry, your voice is not clear.
Like suddenly the same code. Oh, okay. Is it clear now?
Yeah.
Okay. So yeah, suppose we want to code edit distance. So what is edit distance? Edit distance. It takes a string, another string, and it returns an integer with the minimum distance. Let's go back to the reference. Yeah. So suppose this is how we are going to do the edit distance. So what will our final output be? Our final result will be dp of, I believe it's n, n, right? Does everybody see why this is our final answer?
Yeah.
Yeah. Okay. So if that's clear, yeah, we only have 10 minutes, but so I will probably need to hurry this. Yeah, try to do this in time. If not, maybe we'll have to hold an extra. Okay, let's see. We'll think about that. Yeah. So edit distance. So yeah, it will be dp of n and m. So that's basically what? That's basically the last element in our. What's the bad place to put it? That's basically the last element in our table, right? The dpn, n. You want this element. So suppose we have this dp table, which is a list of lists, and we essentially want the last column of the last row of dp, right? This makes sense? If it doesn't make sense, can someone tell me like where they're getting stuck?
Is it equal to dp mn n? Or
yeah. So what I want is dp nm, like because I first index by the row and then the column. And then what is this? A dp n is it's a row, right? A row of elements. Okay. So dpn, and I want the last element of dpn, right?
Yeah.
Okay. So, and then, so basically I want the last column of the last row of dp, right?
Yeah.
So then does last of dp make sense?
Yeah.
Okay. So yeah, let's suppose we have the dp table, and then it's just is equal to last of dp, right? And now we are going to define the stuff. Okay. So yeah, let's define dp. It is a list of it's a 2D array, so it's a list of lists. Does that make sense? Because so essentially how we'll be storing it is, oh god, yeah. So dp equal to this will be our first column, first row, then a second row, and then dot 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 our final row. So it's a list of lists. Do you see why?
Yeah.
Does this make sense to everyone, or am I audible?
Yeah, you're audible.
Yeah.
Okay. Like, is anyone having problem with this definition?
So in this, these inner list are the rows of the
Yeah,
first table.
absolutely.
Yeah.
So do you see why we would want the last element of dp? Like, so the last element of dp is this, which is the nth row, and then the last element of this list is this, which is the mth column. So does it now make sense why we want last of dp?
Yeah. Yeah.
Okay, very cool. So now let's construct dp. Okay, so what will the first row of dp be? So essentially, oh wait, row. Yeah, so that will be this thing. So I have 0 here, and then I have 0, 1, dot, 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 till n. So that will basically mean the edit distance between the empty string and some other string. What's this? Edit distance are just the number of operations required to go from the empty string to this string.
Length of that string.
Absolutely. So essentially the first list will be 0, 1, dot, dot, dot till n, right? Because I want to match that. That makes sense? Because I want to match the empty list with whatever the first j elements of bs. So it will just be j insert operations. Does that make sense?
Yeah.
Just a sec. In this whole thing, like your target string is ending up as the empty string in every case. Shouldn't your target string end up as the second string or not?
Yeah, so our target string is the second string, and we're starting with the empty string. So we would want to do, so suppose this string is of length k. Then we will have to do k insert operations to get to this string, right? Does that make sense?
Yes, but I'm not sure what your motive is. Because in this case, like you're doing the edit distance from any string to 0. But I'm not sure how that, right? Like from any string. Like when you take last of this table.
Absolutely, absolutely.
The distance from a string to the empty string. So where are you introducing the second?
Wait. I just want to calculate the first row of this. The last of dp is the nth row with the mth column. So nth row will mean first n characters of AS matched with the first m characters of BS. So that's what we want. And the 0th row would mean the first 0 elements of AS matched with the first whatever the kth
okay,
column
okay.
will resurrect. So yeah,
Thanks.
does that make sense?
Yeah, I got it.
Okay, cool. So yeah, so our first row will then be 0 dot 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 m, right? That makes sense.
Sure.
Okay, very good. And then we will have to add some values. And okay, so let us first define the part which is simpler. Okay, you know what? Actually, we are slightly okay. Yeah, we actually don't have. We only have 3 minutes in this meet left, according to sir. So if I just try this. Arindam, we can have free Zoom meetings for 40 minutes. So will I just use my account to start another free meeting in case this overshoots? Does that work for everyone? Okay, cool. Then I'll just post that new link and then sign. Yeah. I'll just stop sharing. Yeah, just stop sharing. Keep it stop sharing. I need to leave now. Thank you very much for the video. Oh, that's unfortunate. Okay. Yeah. Like, could it be?
So do we need to leave this meeting and then go back to that link?
Yeah. You'll have to leave this meeting and then join with the link I've sent in the chat. Yeah. Cool.
Yeah.
Okay. I'm just making a step. Okay. Yeah. Let's go with this room. Yeah. What was your question?
Yeah, your voice is breaking actually. Hello?
Yeah, I think he'll rejoin in the.
Yeah. My net got cut for a moment. Yeah. Yeah. Go ahead. What was it out again?
Yeah, so it's like over here dp I-1j. It's like like what to say. We remove the first we take the first I elements and then the j elements of the second list. I mean, like first I-1 elements of the first. But shouldn't we take I-1 elements of like last I-1 elements? Like because we are like taking the tail.
Oh, yeah. So essentially, yeah, I was sort of hoping no one would notice, but yeah, this is actually, we're going from the first element to the last, like we're doing that. And this is different. Like so how do I say? So this was like comparing the first element, and if they are not the same, then I calculate the distance between the tails. What this DP recurrence is doing is it's comparing the last elements of the list. And then if they're not doing the same, it's considering the first of them. Like
Okay, from the behind we are doing.
Yeah, exactly, from behind. Yeah.
Okay.
It's basically the same thing, just in a different order.
Okay.
Okay, cool. So yeah, let's go back to this. So okay, yeah. So our recursion, this will be exactly analogous to open. Yeah. So firstly, we want to input. Yeah, I'll just define it and then we can get into what is happening. Okay. So recursion. So our values here are AI, BJ, and then DP I-1, J-1, and then DP wait, no, up is, yeah, DP I-1 J, and then DP I and J-1. This is all the inputs I need for the recursion. Where a recursion was this thing. This, oh boy. Yeah, I don't know how to have it. Yeah, so this is what we want to do with our recursion. Oh dear. Yeah, this thing. So the values we need are ASI, ds of I, dpi minus 1 comma j, dpi minus 1 j minus 1, and dpi comma j minus 1. So we are taking AI dj, yeah, AI dj, dp I minus 1, j minus 1, and these values. So why we are taking the inputs, does that make sense?
Yeah, I'm not sure like what's exactly going on here.
Oh, okay. So basically we want to compute dp I comma j, and to compute dp I comma j, I just want to see what values I require. I require this value, I require this value, and then I require the dp I minus 1 j minus 1 value, and this and this and this, right?
Yeah, yeah.
Okay. So like this is just simplified. So yeah, recursion. So yeah, this is what we want to do with the recursion. And then suppose I actually like, let us put simpler notation, AB. So D stands for diagonal because I minus 1, J minus 1 is diagonally up. And U stands for up because I minus 1 is the upper row. And L stands for left, which is J minus 1, which is the previous column. This is just notation. There is nothing important about this. And okay. Now let's go back. So what was our recursion? If ASI equal to BSJ. So if A equal to B, then what is it? It's dp I minus 1, j minus 1. So that's the diagonal. Else, what do I want to do? So I want 1 plus the minimum of these values. So the minimum of, okay, since this is Haskell, yeah, so minimum of diagonal and up, and then minimum of that and L. So does the recursion definition make sense? It's a bit complicated, but it's basically the same thing that we defined here. We're just doing it in Haskell terms. If anyone has a problem, you can tell me.
Also, it's like like in the like that line dp double colon 0 dot m. Like I'm not sure. We have never used that. This kind of. I'm not sure what this means. Like okay, it's just.
Yeah, that's fine. That's fine.
Okay.
So does the recursion function make sense?
Yeah, yeah.
Okay, very cool. Then okay, now let's keep this for now. And okay, since we're going to be using n and m, we'll just define n and m first. It's length of AS and m equal to length of DS. DS. Yeah. Okay. Okay. Now what we want to do is okay, so this is the hardware part. Yeah. So now what we want to do is okay, so notice that to calculate dpij, I need at most the values of the previous row. I am never going beyond the previous row, right? That makes sense.
Yeah.
Okay, cool. So yeah, that's yeah. So now what that means is given the ith row, I want to calculate on its row. This is what I want to do. Okay. Oh wait. I think my internet is answered. Am I audible? Oh dear.
Very barely.
Okay. Oh, sorry. Yeah. Is it clearer now?
It's clear for me.
Okay, maybe not. Oh, okay, that's good. Then I'll continue. So yeah, what I want to do is, given the ith row of the DP table, which is this thing, I want to compute the I plus 1th row. Okay, so now what's the first element of the ith row? That is dp of 0, I. Can anyone answer this? Oh wait, no, sorry, I wrote it wrong. It's I. The ith was first element. Okay. dp of I, 0.
That should be I guess.
Absolutely, is equal to I. So yeah, so now let us start. So I want the next row given the value of I and the previous row. Oh, it's double colon. And I will return the next row. Let's type int. Very cool. And next row of, suppose the value I, and suppose we have the previous row equal to, so the first element, as one of you said, is going to be I, right? Is that clear to everyone? Why the first element is? Does anyone have any problem with this definition?
I think it's fine.
Oh, show the code. Yeah. Oh, wait. Yes. This part. I is to, and then we'll add the rest then after that.
What is previous row? I mean the PRB row thing.
Oh, previous row will be the ith row. So I want to compute the I plus 1th row. Given the, okay, so maybe this is not good notation considering we are doing I. So let's just make it the I minus 1th row, calculate the ith row. Okay, so I want to calculate, yeah, so the previous row is the I minus 1th row. Okay, and from this I want to calculate the ith row. And as one of you pointed out, the first element of the ith row will be I. So far, does this make sense?
Yeah.
Okay. That is good. Okay. So now dp of I, j is equal to what we know, it's recursion of, okay, again. So as of I, ds of j, and then we need to pass this. So first is a diagonally upward, so that's dp of I minus 1, j minus 1. Then we have the upward, dp of I minus 1 and j. And then we have the one to the left of it, which is dp of I and j minus 1. This is just definition, right? Does anyone have any problem with this? Oh, wait, someone is on the chat. Okay. Does anyone have any problem with this definition? Okay, then I'll assume no one has a problem. So yeah, now let's convert this into terms of the, oh, wait. Why is support? Okay, yeah. So in terms of next row and previous row. Okay, so this will be the jth element of next row. This is fixed. This is, we'll have to calculate. And then this is j minus 1th element of the previous row. And this is the jth element of the previous row. Does this make sense? The fact that this is the jth element of next row, and this is j minus 1th element of previous row, and this is jth element of previous row. Like, tell me if something, like if I'm not being clear about it or if it's confusing, because this is the important part. Like, this is how we're going to use it for the syntax. Oh, wait, am I audible?
Yeah.
Okay, good. So I'll assume everyone is understanding the definitions, which is great, honestly. Okay, so then let's rewrite this. So what do we have? We have CNT row of j equal to recursion of just a second. Yeah. Okay. So now let's just keep it adjusting now. And then we have previous row and then j minus 1. Here we row j and here. Does this make sense? Oh, just repeat that one. Does anyone have any doubt with this definition?
Yeah, shouldn't we? No.
Yeah, go ahead.
It's fine.
Okay. Okay, cool. Okay, so yeah. Now we will try to do all that weird stuff. Okay, so okay, now let's actually go one more step. So notice that for the whole row, recursion's first argument, which is okay, let's use the bracket here because we often do brackets then, which is recursion as bang bang I. This is fixed, right? And then our next problem is this, and then we have this zip tree. Okay, yeah. So this is actually abusive notation. Okay, so let's not use zip tree yet because zip tree is actually on a list. So we'll not do that. And the -1 previous row. Okay, so that's basically the same thing I've been doing. Second, but yeah. Row. And then say -1. Okay. Yeah, so that part is clear. So CNT. Yeah. Now. Okay, so now we will have to do that weird business. Okay. Yeah. Okay, so let us consider this one, BS. So like for CNT row, for 0, I will pass. Okay, no, for 0, I will not pass anything because for 0, I don't want anything. It's blank because for 0, it's already defined as I. And for 1, I will pass the first element of BS. And for 2, I'll pass the second element of BS. Dot, dot, dot. For M, I will pass BS of M minus 1. Right? This makes sense?
Can you repeat what's going on?
Oh, okay. Yeah. So, okay. So firstly, we were defining CNT, the jth element of CNT row, which is essentially DP of I comma j. We did this thing. Then we simplified it to in terms of CNT row and previous row. And then we got this. Yeah. So now what I want to see is, like, given this value of j, what is the value of BS of j going to be? Okay. So for CNT row of 0, it's empty because like CNT row of 0 was defined to be I believe. Some of one of you, yeah. So CNT I of 0 is I. That's fine. And then for CNT row of 1, it will be the first element of BS. Then it will be the second element of BS for CNT row of 2. And then for CNT row of M, it will be the last element of BS. This is just the argument being used for calculating CNT row of J. Does that make sense?
Yeah. Okay.
Okay, cool. So as you can see, we haven't been entirely accurate with this. This will actually be BS of J minus 1 because like from here it's clear, right? Because the mth element is actually M minus 1th element of the list, like index M minus 1 in the list. And similarly, this will also be the same. It will actually be I minus 1. We were just abusing notation. Okay, so far is it clear? Because like we are doing lots of complicated steps one at a time. So does anyone have any doubt with this, or it's not clear to them? Okay, then I'll assume no one has a doubt with this. So where does that put us? That puts yeah. Okay, so yeah. So yeah, so we have this thing. And then now consider for CNT row of 1, what this will be, this 3 to 2. Oh boy, yeah, just consider it. Okay, so previous row of J minus 1. So I will first have ERV row of 0, comma, ERV row. Okay, so next is PRV row of J, right? Yeah, PRV row of J. And then, oh, J here will be 1. And then we have CMT row 0. This makes sense for 1. And then for 2, we will have PRV row of 1, comma, PRV row of 2, comma, CNT row of 1. Yeah. Does this make sense?
Yeah.
Okay, cool. So now we are going to do some weird zip business. Okay. So first let us consider this thing. Zip 3 up. ERB row. Okay, so this isn't Haskell syntax. Let's do Haskell syntax. Tail up. Oh god, I keep forgetting stuff. PR0 and then CNTO. So consider this equation. Okay, the zip3 thing. And then is it fairly clear that zip3 of J will be equal to this pair, like this tuple, this PR0 J, this thing? Like zip3 of J will be basically PR0 of J, PR0 of J plus 1, and CNTO of J. Is that fairly clear? If it's not, you can tell me, because we're like gradually, it's okay, very cool. So we have zipped these values into a list, and similarly, okay, so the list compilation of this is just BS, right? So for 1 it's BS0, for 2 it's BS1, for M it's BS. So if we consider BS and then a CNT row of I, it's just BS of I minus 1, whatever. That makes sense? Because like essentially what we're going to do is like we're going to, instead of defining it for each point, we're going to put it through a zip with function. So we first want to convert these arguments into a list. So the BS arguments, the BS arguments we will compile into the string BS itself, because it's BS0, BS1, BSN. And this tuple arguments, it is compiling into this thing, PRV row, tail PRV row, and CN tail row. Does this make sense for everyone? Okay, I'll assume it makes sense for everyone. So what we have is BS, and then we have zip3 of, okay, no, why are we having it here? So yeah, so yeah, let's just keep some space, and I have BS, then I have zip3 of, okay, yeah, zip3 of the previous yeah, the PRV row, previous row, the tail of the previous row, and then I have what so the, what can I say, yeah, so basically same row. So next row of I, like, because it's not exactly defined as next row, so it's basically just this thing, like this list, and so I want to zip3. So like this, does this equation make sense, that it's a list version of the set of arguments we pass to each, it's the J element. Like for this thing, it's like this compilation. We'll just put it into a list. So that will be BS and this zip3. Does this make sense? Okay, I'll assume it does.
Can you explain again why the BS is there? Like, I'm not exactly clear.
Oh, okay, cool. So yeah, let's again do this part. I think no, it's fine. I'll draw. Yeah, so CNT row, the J plus 1th element is equal to recursion of I minus 1 J minus 1, and then this tuple Okay, so first of all, does this definition make sense?
Should it be G instead of J plus 1?
Wait, can you go again?
Should it be J? Should it be J instead of J plus 1, like CNT row, ban or J like, plus 1?
We are calculating J plus 1. So for that, we need the left value. So it's CNT.
Okay, okay.
Okay. So this definition makes sense. If not, you can tell me like if it's confusing. Oh wait, am I audible?
Yeah.
Okay, good. So, yeah. Now essentially, what we want to do is
Your voice is breaking right now.
Right? So for G values of this will be, oh, okay. Is okay. Wait. Is it better now?
Yeah.
Oh, okay. How about now? Can you hear me clearly now?
Yeah, it's fine.
Okay, good. Okay. So for J equal to 1 to M, what will be the value of BS of J minus 1? It will be BS 0 and then BS 1 till ... BS of M minus 1. Okay. Does this make sense?
Yeah. Also,
okay,
like,
so if
one more thing in the like 3 tuple, like, should it be previous to bang J plus 1? Because it's like
okay,
the
yeah, thank you. Yeah, absolutely. Yeah, good. And oh no, this yeah. Okay, no, yeah. So the previous column and yeah. Over. Okay, makes sense. Okay. Thank you for that. Yeah, it will be J plus 1. Yeah. Okay. No. In that sense. Yeah, and then I think actually this is also not right. I think it's just the I and Z. No, this is I minus 1. That's fine. Yeah, this is just BS of J because we're calculating that for J plus 1. So yeah, from 1 to M, it's BS 0, BS 1 to BS M minus 1. This makes sense?
Yeah.
Okay, so I just want to put this in a list, and like if I were to put this in a list format, like just one element after the other, it would finally amount to BS.
Yeah.
Like you don't need to worry about why we are doing this for now. It's just tell me if this makes sense. Like if I'm putting this in the list, it's compared to BS.
Yeah.
Okay, cool. So now we want to do the same thing with this second argument. So I want this to do, and so firstly, what we'll have is a PRV row of J, and then this J is going from 0 to M. So this will just be all of PRV row, right? Because so this will go from this J goes from 0 to M. So here PRV row will be first it's 0 and then ... all the way to M. So PRV row is like this will be the whole of PRV, right? The first argument.
Yeah.
Okay, and then we want PRV row of J plus 1. So that will be the tail of PRV row because I just want the next argument. Does that make sense?
Yeah.
Okay, cool. And finally, we'll again have CNT row itself because like 0th element of CNT row for J equal to 0. So does this mean if I was to compile them in a list, this would be BS and this would be this thing, this PRV row, tail, PRV row, and CNT row.
Yeah.
Okay, so now we're almost done. That's okay. So then this thing makes sense that the arguments in a list format would be this. BS and then zip3 of previous row, tail of previous row, and then this next row of IP below. Right? Okay, so I'll I'll just assume makes sense. So now finally what we want to do is to the ith. Okay, I is a bad notation. Let's take it K. To the kth element in this weird tuple, I want to apply recursion of AS and then I minus 1. Why? Because this is what I want. So to the ith element, the kth element, like which will be this thing basically, I want to apply recursion of AS minus 1. Does this make sense? If there's a problem, you can tell me. Okay, then I'll assume that this makes sense. So I want to apply a recursion of AS cos minus 1. No, cos not. So I minus 1. Yeah. So I want to apply this function, this recursion of AS I minus 1 to every element in this list. Right? So that's that. And how do we do that? So Sir already taught us that. That's with the zip width function. So what the zip width function will do is it will map this function, the recursion of AS I minus 1 to like the corresponding j comma jth element of these lists. And that will essentially be my j plus 1th value in CNT row because I'm already setting the 0th value as I. So this is, I think this is probably the most complicated step. So if you want me to repeat, I can repeat.
Yeah, can you repeat
First
it?
of all, am I audible?
Yeah.
Okay. Did you ask me to repeat?
Yes.
Okay, good. Yeah. So is up to this part clear? To each element in the list, I want to apply the recursion AS. I want to apply this recursion AS of I minus 1.
Yeah.
Okay, very cool. And okay, so let us go back to basics. What does zip width of a function, this one, and this two do? It's essentially f of ls1 of 0, ls1 of ls2 of 0, comma f of ls1 of n, ls2 of n, right? You know this by definition?
Yeah.
Okay, cool. So what will then this function do? Like this weird equation, zip width. So firstly, it's going to apply this thing, recursion AS I minus 1, which is what we want to apply to the two arguments. One is BS, the other is this weird 3 tuple that we computed. So okay, so what is okay? So yeah,
I actually got it.
Okay, it makes sense. Does it make sense for everybody else? Okay, since people are not unmuting, I'll just sort of assume that it does. Okay. Oh yes. Okay. Very cool. Then yeah, I believe that. Is someone?
Please repeat again.
Oh yeah, sure. Okay. So up to this part, is it clear that to the kth element of this weird tuple, I want to apply recursion AS I minus 1?
Yeah.
Okay, very cool. So we have seen that this is what zip does. Suppose I have ls3 equal to sequence. So let us see now what will be the jth element or kth element of ls3. So that will be equal to f of list 1 k and list 2 k, right? And now let us see what it will evaluate to in our code. So our code is, okay, first is f is this thing, right? So let us replace that. So recursion. Okay, so first, this thing makes sense?
Yeah.
Oh, good.
Yes.
So first, our f is recursion of as I minus 1. Okay, now ls1 of k. Our ls1, yeah, okay. Our ls1 is here. Oh, wait, it's bs. So yeah, so that will be bs of k, right? Because it's from definition, right?
Yeah.
Okay, cool. And then what's next? Okay, so zip3 of PRV0, tail PRV0, and NX3. Okay, so PRV0. So firstly, I will have PRV0 of K, right? Because it's just the kth element of this thing.
Yeah.
Okay, cool. And then next we will have, since we are taking the tail, it will be PRV0 of K plus 1, right?
Yes.
And finally, it will be CNT row of K, right?
Yeah.
Because, okay, cool. So we, this is the ls3 of like whatever the kth element of the zip width will be. And we already know from definition that this is essentially equal to CNT row of K plus 1, right? Because that's exactly how we defined our recurrence relation, this thing. Does this make sense?
Yes.
Okay, very cool. So now, so basically, okay, so let's actually make this, let's call this weird list equal to zip3, then this thing. Okay. So then what's then weird list? Okay. Yeah, weird list of K is essentially equal to CNT row of K plus 1, right? Does this make sense? Because weird list is essentially this thing. Like weird list kth element is just this thing. So we evaluated that to be equal to CNT row K plus 1.
Yeah. Okay.
Okay, cool. So yeah. So like, so essentially what we can say is then CNT row equal to the first element of CNT row, which is I, is to weird list. Okay, no, wait, let's go one more step. Yeah, so CNT row equal to the first element we know is I, is to CNT row of 1 is to CNT row of 2 is to the vector 2 PM. Let's say CNT row of n empties. Okay. So what we have computed is this is weird list 0. This is weird list 1 and dot dot dot. This is equal to weird list of n minus 1, right? Just from definition, does this make sense? Am I audible? Oh boy.
Yeah,
Yes,
you're
yes.
audible.
You're audible.
Oh, I'm okay, cool. So whoever was asking,
Oh, can you
does
just
this,
repeat
yeah.
what you said in the last? I had a network
Okay,
problem.
okay. Yeah. Does this make sense? Weird list of k is CNT of k plus 1.
Yeah, yeah.
Okay, cool. So like essentially what we're doing here is, so CNT row is the first element of CNT row, added to the second, to the third, to the dot dot dot, to the last element of CNT row. We are just writing CNT row this way. Okay.
Okay.
Okay, good. So now the first element, one of you already computed that it's equal to I. Okay.
Yeah.
Okay, cool. So the first element is I, and then CNT row of 1, CNT row of 2, dot dot dot, to CNT row of n. And what we have seen here is CNT row of 1 is equal to weird list of 0, right?
Yes.
Okay, so we can write it as I is to weird list of 0 and then weird list of 1 dot 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 to weird list of m minus 1, and then just empty this because like it's just this is a list, right? Does that make sense? Like
Yes.
we're just rewriting these elements. Okay, cool. So then essentially we can write it this way. Oh, wait. Yeah. I is to weird list because it's just that like we are concatenating I to weird list, like we're adding I to the front of the weird list. Does that make sense?
Yeah.
Okay, cool. So that will just finish our thing. So next row is equal to this, is to weird list. And weird list is defined here. Zip with blah, blah, blah. So yeah, now we'll just replace the definition in its place. So this to I is to this weird combination. Oh, wait, yeah, okay. And this should ideally work. Yeah, so let's just comment out the first part. Okay, let's just make this a distance. Yeah, cool. And load the distance. Okay, something is wrong, possibly incorrect. I'm listening that it's okay. Let's missing something. Wait, what is okay? What am I doing?
There is an extra colon, the line above.
Oh, right. Sorry. Yeah. So, okay. Yeah, we haven't still finished. So, DP, and then what we want to add is next row of. Okay. So, yeah. I'm sorry. We actually haven't finished. We just computed next row from previous row. So now what we know is DP. We have the first row of DP, right? And then to that, I want to add. Okay, so let us again go by the long method we did. So DP equal to next row DP of I minus 1 and I, or wait, what order were we passing next row? Okay, so first it's going to be I. sees why this is the case? Okay, I'll assume everyone does. So yeah, and then okay, so again, so I ranging from 1 to n. Yeah, I ranging from 1 to n. This thing becomes the list 1 dot dot n. This thing becomes just the list dp. Right? Does this make sense? Okay, hope it does make sense. So again, we're going to do exactly what we did here with the zip width thing. So I'll just zip width of the function nx0. And then we have this list, which is 1 to n. And then we have dp itself. So can you see why dp should be dp0 and then dp of I is this thing? Does that make sense for everyone? If it doesn't, like, we can again go through each step. It's fine. If it doesn't, like, if anyone is having difficulty with this definition. Okay, then I assume everyone sort of understands it. Oh, yeah.
It's just the lazy evaluation thing, right? Like this one. It's like
Yeah, so we are using the dp in the definition of dp, right? That's what you're saying?
yeah.
Yeah,
So
it's lazy evaluation. We actually also did lazy evaluation here because in CNT row, we are again like passing CNT. So like for this definition also, for defining CNT row, we were using CNT row. Okay. So we are doing lazy evaluation in all these cases. But yeah, that's a good catch. It is lazy evaluation. Okay, so then let's go back here and then dp is, so the first row of dp, again, one of you calculated that it's just going to be 0 to n. And then what do I want to do? I want to do zip width. What's my function? My function is next row. What's my list? It's going to be 1 to n. And finally, I'll pass dp. Does this make sense for everyone? If it's not, I can again go through it. Oh, there's something. Okay, yes. Okay, then I'll assume it's more respect for everyone. Read it. Oh boy. What's no? Oh, it's probably yeah. Okay. Okay, no. Something stupid. Okay. Minimum. Okay. Oh, okay. Yeah, okay. So it loads. Okay. I can't actually convince you that our program is correct, but Suresh sir gave me this like this, it was a previous assignment from like one of his previous Haskell courses, and they gave edit distance as an assignment problem. So we have these two sample cases, so we'll just try them on these for now and satisfy ourselves. We can work with that later. So edit distance of smitten and city. Yeah, that's 3. And let's do nematode knowledge over. Edit distance of nematode knowledge and empty bottle. Empty bottle. And that's 12, which is also what we done. So if you guys want, I can send you this whole PDF or just the question under code, but okay. So that sort of concludes what we are trying to do. So does anyone have any doubts? No doubts. Thanks. Okay, that's cool. Now stop sharing. And, thanks for attending. I guess very few people have left, but yeah, thanks for attending. If you have any doubts, you can.
OneNote file?
Which file? The OneNote file. Okay. Yeah, sure. I'll share.
Yeah, and the code.
Okay, so
You
the
can just,
program and the OneNote.
Yeah,
text it
program
in
and
the
the
text box, and I can copy it to the WhatsApp if you wish. Otherwise,
Oh, I'll just upload it on Moodle if that's fine.
okay.
Okay, cool. Yeah. Thank you. Thanks for attending. Yeah, I'll end the meeting now.